In this video, we're going to look a little bit at vector addition. This is one of those things that you might have seen if you've worked with vectors before, but we're just going to emphasize some notation things and talk a little bit about why you would ever do vector addition. So I'm just going to do the algebraic definition, and then we'll look at some applications of that. So I'm just going to start with two generic vectors in R3. Again, using good notation here. My V with the barb over it, or bolded, you would see that in the textbook, type bolded to indicate that it's vector, brackets here, and three components in R3. And then another vector here. Since we're going to talk about adding vectors, we need two of them. All right, so I have two vectors here, and what we want to talk about is what does it mean to add those two vectors. So the definition of adding those two vectors is equal to, by definition here, I'll use that notation quite a bit, is that we're just going to add the corresponding components. So this is an algebraic definition of what it means to add two vectors. You're going to add the corresponding components. So in the first component, you'll add V1 plus W1. And then in the second component, V2 plus W2. And then in the third component, V3 plus W3. So algebraically, this is easy to do. It's just adding numbers. The question would be, what does it mean, and why would you ever do this? Let's just look at a little example here of a couple vectors, and we'll draw some so we can kind of think about what is happening here with these two vectors. And that maybe helps lead a little bit to why you would ever do this. So I'm going to just do this in R2, so it's a little easier to draw and see what's happening geometrically here. So I'm going to start with a vector. Let's start with this first one. V is, say, 1, 2, and the vector W is, let's say, 3, negative 1. Okay, and so if we add those two vectors, the sum of those two vectors, we're just going to add the corresponding components here. So V plus W is 1 plus 3 is 4. And then in the second component, 2 plus negative 1 is 1. All right, and then to think geometrically about what does that mean to add those vectors, I'm going to draw these actually in a little bit different way than we've been drawing the vectors. I've been drawing them mostly with their tail at the origin in standard position. But this really indicates kind of why you might want to add these two vectors. All right, so let's look at a coordinate system here. All right, and so I'm going to start with my vector V in standard position with its tail at the origin, so over 1 up 2. So there's my vector V. And then what I'm going to draw is from there, I'm going to draw my vector W. So from this point, that is over 1 up 2, so my initial point here is at the terminal point of V, I'm going to draw my next vector W. So from here, I'm going to go 3 units right and down 1 unit. So from here, I'm going to go over 3 and down 1. All right. And then if we look at the origin and the terminal point of where this vector that is V followed by W is, you can see that that gives me my vector V plus W. So if I draw that vector V plus W with its tail at the origin, you can see that it ends up there. And so one way to think about this, and geometrically what it means to add vectors, is to think about that you might be doing something like moving along a displacement that is along this vector, followed by a displacement along this vector, and then this vector would give you your total displacement from the starting point to the ending point. There are other things that combine this way in physics, but combining displacements, one vector followed by another vector, is one important application of vector addition. So combining displacements, that would be if you're moving from one place to another, that vector would represent your displacement, and then another displacement, and so that would represent your total displacement. Forces also combine this way. That's a really common way that you might have worked with vectors before if you worked with them in a physics class, is that if you have several forces acting on an object, this is the way forces combine acting on an object. And so that also leads to another way that you might use addition of vectors. If you're working with something in physics or in statics where you don't want things to move, you want things to stay stationary, you want all of those forces to add up to 0. And so sometimes that's another important application of vector addition, is to make sure that all the forces add up to 0 so that there would be no displacement on that object, so that it would stay where it's supposed to be. If you're designing, say, a bridge, you don't want it to move. All right, one other application to do with vector addition is really a more mathematical application, which we will see a little bit in this class, but you'll also see some more if you take a linear algebra class and or a differential equations class. And that's called a linear combination of vectors. There are a few problems in your homework that talk about linear combinations of vectors. And really, in the applications that we are working with right now, we are just doing this very mathematically. It's not really in terms of applications right now. It's just they're asking you to find a linear combination that satisfies a particular situation. A linear combination is really a sum of scalar multiples of vectors. So I perhaps have two vectors here and maybe two scalars, and we can talk about a linear combination of vectors where we talk about a scalar times a vector plus another scalar times another vector, and then maybe we even have a third scalar times another vector or whatever. But this is what's called a linear combination of vectors. And we use this when we do ways of scaling things and combining things. And so there are a few problems in your homework that talk about this linear combination of vectors. It's really an application of adding vectors. And that leads me to one other thing that I want to talk about in this video. We'll look at some examples of this in some later videos where we look at examples of doing calculations with vectors. But one other thing to talk about, so we've talked about multiplication and addition with vectors. Other operations that we haven't talked about yet are subtraction and division. So we do have subtraction of vectors, but if you use this idea of a linear combination of vectors, you don't really need to define subtraction of vectors separately from addition of vectors. You can think about subtraction of vectors. So you can think about two vectors being subtracted as really just 1 times the first vector plus -1 times the second vector. So you've got a linear combination of vectors here where your scalars are just 1 and -1. So it's really just combining addition and scalar multiplication, so you don't need to define subtraction in any way. There is no such thing as division of vectors, so that's something we won't be defining. There are some other kinds of multiplications of vectors, which we will look at in later chapters in the textbook. So we will look at some other kinds of multiplications of vectors as well. All right, in the next video, we'll look at some examples of using some of the calculations we've already done with vectors and a few applied problems with some of those.